Hello and welcome to this session which will cover dynamic content insertion into live streams across Smooth, Dash and HLS. Before I get started, let me introduce myself. I'm Nigel Harniman. I've been working in online video for many years, initially at Sky, focusing on Sky Go and Now TV, more recently at Bright Cove, working with many broadcasters and publishers, and this year I switched to a great company based in London called M2A Media, where I've been working on our live product, specifically the new features in support of regional and targeted content insertion. Let's start by reviewing what we mean by content insertion, why it is required, and how it has been traditionally done. As a broadcaster, you may acquire content rights on a global basis. As this diagram shows, we've got an example which is UK, Italy, Colombia, USA and Japan. Maybe the rights require that you insert obligated content which is different in each region. In addition, you want to insert promotional items into the stream that have regional relevancy. You may also opt to have paid for content such as commercials or sponsorship idents, which again may be different on a region basis. Traditionally, this is implemented by taking the common world feed from the MCR into separate TX playout systems for regional content insertion, and then delivering through a replicated live streaming workflow on a per region basis. The live streaming architecture that we deploy for customers, which is a very typical configuration, consists of cloud contribution, encoding, packaging and distribution components. These are deployed in a multi-region resilient manner. Our orchestration layer provisions the resources based on the event schedule that the customer supplies. And for some of our customers that are operating multiple concurrent events at a very high frequency, we might be doing this multiple thousands of times per month for them. If we zoom out, we can see that for a customer with, for example, 50 concurrent channels or TX chains and a single output, the resources required look like this. But if that customer was to do 8 regional outputs, then it multiplies up pretty quickly. I think you can agree that that's an awful lot of resources that need to be provisioned and the cost will be significant. So we wanted to look at other ways of doing this. So the first thing we looked at was the existing technologies that can be used to insert content in the OTT domain. Typically, these are used for ad insertion. Client-side ad insertion relies on code. Typically it's a library or an SDK to run within the player in the device. These types of solutions are widely supported for desktop and mobile devices, but they're less so in the TV and the set-top box type device footprint. Sometimes this is because those devices don't have the processing power that's needed to implement the multiple players required for a seamless experience. Sometimes it's because the vendors don't think the target market is big enough and they're not investing in it. But in any case, a client-side solution requires extensive per-device development and testing, which in itself can be resource-intensive. In addition, it's quite easy to block ads at either the device or at the premises edge, i.e. on the home gateway device. Thus, that's not really a viable solution for inserting legally obligated content. Server-side does provide a more robust solution. However, the commonly available platforms only support HLS and multi-period Dash. Smooth is definitely not an option with those solutions. These platforms are also typically aimed at targeted ad insertion, and thus they manage a session per viewer. And the costs that they charge reflect this. So if you have 1 million viewers across 10 regions watching an event, you're going to be managing 1 million unique sessions when really you've only got 10 variances. And it's because of that the cost becomes uneconomic quite quickly. So the approach that we came up with and we've implemented into production allows content to be inserted post-packager in an efficient manner. For ABR formats, the packager output is segmented. We ensure though that the segment durations are chosen to align audio samples and video frames on the segment boundary. So for 25/50 frames a second, this equates to a multiple of 1.92 second segment durations. And for 30/60 frames a second, This equates to a multiple of 3.2 seconds. We also need a dynamic playlist to control all of this. A dynamic playlist is created per regional variant for each event. This is supplied from the customer scheduling system, for instance, What's On. It contains the list of breaks and the unique asset identifiers to be inserted for each break. Separately, each asset is delivered via a dedicated VOD workflow that ensures it is conditioned to match the live stream exactly. So it has the same segment size, the same frame rate, bit rate, and encoding profile. We then issue separate URLs for each region, and we do this using a query parameter for the unique identification. Segments are then dynamically and selectively replaced with the relevant segments from the VOD archive. Splicing is triggered via SCUDdy35 markers embedded within the source stream. In addition, the SCUDdy markers are selectively included in the output based on the playlist metadata, allowing downstream placement opportunities, i.e. if the customer wants to, they can then use a targeted ad insertion on top of our solution. Because we have to do this differently for each of the streaming formats, I'm now going to dive into that detail. HLS is the easiest stream format to support. HLS allows for manifest manipulation, i.e. replacing segment URLs with references to VOD segments. The manifest manipulator is driven by the presence of the QOut, QIn, and date range tags. Date range is required for the ID of the ad break. This is used to look up against the playlist and derive which VOD content to insert. In this example, a 9.6 second break is filled with 2 segments of asset 1 and 3 segments of asset 2. Note the presence of the discontinuity tag to signal to the player that the media timestamps and encoding profile may change on content switch. For this break, the Q tags are also written into the manifest for further downstream placement opportunities. Caching is vital in this solution to ensure that the manipulated manifests are requested as few times as possible. Multi-period dash can allow a similar manifest manipulation approach, but to support single period dash and smooth stream, we needed to come up with something different. Given smooth manifests are only obtained once at startup, and single period dash does not facilitate changing the segment template during an event, our solution requires on dynamically replacing the segment contents themselves rather than referencing a different URL. The segment rewriter's role is to take each dash and smooth segment request and then either pass through the underlying live segment or, if we're within an ad break, rewrite the required VOD segment to match and return that instead. We need to ensure the player is unaware of the change, and so therefore the MP4 boxes need to match exactly and be part of the contiguous stream. The segment rewriter simultaneously obtains the original live media segment and the VOD segment if it's going to do a replacement. It then compares the encode profile, so bitrate, frame rate and encoding parameters between the two. If they're not the same, it can't do anything else but return the underlying media. This protects us from an unexpected misconfiguration and then a stream crash. But if the media configuration does match, it then goes on to rewrite the MP4 boxes to match the underlying live stream, so the ones in the VOD get rewritten. So we retain the decode and presentation timestamps from what was in the original live stream and serve the VOD content with those values. The segment rewriter clearly needs to be performant, and thus in our implementation it relies on the announcement of segment timestamps for replacement and the target contents that need to be inserted by a component called the break watcher. This out-of-band process is monitoring for SCUDdy markers in the HLS stream, and it's building the required data structures in memory, so we've got fast access. Again, caching is vital to ensure manipulated segments are requested as few times as possible. The architecture appears simple, and I'm sure a number of you may take these ideas and try to replicate them, but let me share with you some of the road bumps that we encountered along the way. The SCUDdy insertion system uses SCUDdy 104. It's then converted to SCUDdy 35 as part of the transport stream encoding. This is occurring before the signal reaches our head end. SCSI 104 only supports a duration accuracy of 100 milliseconds. So we found that a required duration of 34.56 appeared in the transport stream with a duration of 34.5. What was then odd is that when we saw it in the actual HLS manifest that we were then going to manipulate, it had a duration of 34.52. Why did it have this? Well, we're operating at 25 frames a second, so we have a 40 millisecond frame duration. And if you think about it, 34.5 isn't a whole number of frames. So we checked with Elemental and we discovered that the encoder was actually modifying the duration to match a whole number of frames. The problem we had though is we need an accurate duration to be able to know what number of segments to insert. And if we got something shorter, we would drop a segment. If we didn't have back-to-back breaks, that wouldn't be such a concern. I mean, if your inserted content doesn't really need the last 1.92 seconds, maybe nobody would notice. Maybe they would. But our bigger problem was the fact that we had back-to-back break patterns. And so what was happening is we'd finish the first break and then we'd return to live for a segment and then go into the second break. And this was known as the flash of live problem. And this is why we had to investigate to this level of detail. So then we had to think about how we could modify this behaviour, because clearly we couldn't change the insertion because SCSI 104 is a standard and it only works to 100 milliseconds. We then looked at the pattern and realised that it was only every 5 segments that the pattern started to repeat itself. So we were able to take a modulus of the actual duration and get a remainder. And from that remainder, we only had 5 possible values that we needed to snap to. We then found out that one of those values was always 100 milliseconds or a multiple of, so it didn't need anything. We then found another one was always out by half a frame, but the encoder, because of its snapping, was actually doing it for us, and so we didn't need to do anything. So in the end, we only ended up with 3 durations that we needed to correct, and so it was very simple to build a lookup table and implement that correction factor. The next major hurdle is that SCSI 35 splice times will not naturally align with the segment cadence. By default, an encoder will condition the stream by inserting iframes at the splice point and altering the segment cadence. Typically, this means extending or shortening the segments around the splice point, which is shown in the top image. However, if the encoder does this, we no longer have the fixed segment durations that the system is constrained to work with. So we requested a feature from Elemental Cloud to suppress segment conditioning. This has been carried over to Media Live as the SCSI 35 without segmentation setting, and you can find more details in the API documentation. But now we have the problem that the timestamps in the SCSI markers, as indicated by the black arrows, don't align with where the splice points actually occurred, which is the red arrows. If we suppress the SCSI markers, that's not a problem. But where we need to pass those markers downstream to other systems like Google DAI, we need to make them match. So this was just yet another piece of code that we had to implement in our manipulation layer to make sure that everything aligned. In manipulating manifests, it's important to ensure they remain spec compliant. We discovered that when the DVR window starts rolling, it's difficult to look at a manifest and know whether you should be in a break or not. And this is especially true when the DVR window is quite short and your break durations are potentially quite long. So we ended up using media sequence numbers to manage this state. And then we also discovered that it was vital to make sure that the media sequence tag that was advertised in the manifest did exactly match the implied sequence number of the first segment, even if it was in a VOD asset. We also had issues when running on multiple origins for resilience that the manifests could be out of step. Effectively, subsequent manifest requests could appear to change history, i.e. breaks would be in one request but not in the subsequent one. And when we investigated this was just due to a bootstrap issue on one of our origins. But we realised that made the process quite brittle. And so for consistency, we moved the bootstrap process into our main orchestration layer and then make sure that each of the origins just gets given the required data. We also had to implement watchdogs on the origins to make sure that any of the kind of watcher processes didn't fail, because otherwise the origin would stop inserting dynamic content. As the DVR window grows, performance needs to be maintained. We've done an awful lot of optimization and a lot of bootstrap work to ensure that happens. We also found out that downstream systems needed both the ASCII and the binary Scuddy marker representations to be rewritten. During initial consultation, it didn't appear that that was the case, and so we'd only rewritten the ASCII. And then during testing, we discovered problems and had to rewrite the binary as well. When handling segment replacement, performance is also a big concern. So again, huge amount of optimization is required. That's why we have the outer band break watcher. Rewriting timestamps was also made hard by threading issues in the library that we initially used. This only showed up under kind of concurrent testing at load. And to solve that, we basically had to write our own code for MP4 box parsing. I mentioned these in passing earlier, but it is vital for Smooth and Dash that the VOD assets are encoded with identical parameters: frame rate, bit rate, codec profile, and segment duration. They need to have a length that is an exact multiple of the segment duration. And when they're served, they need to be encrypted with the same key, because otherwise that's going to cause the players problems. If any of the live stream aspects need to change, such as frame rate, then you're going to need to have a separate copy of the insertable assets. I'm sure a number of you will look at trying to roll something similar out. What I will say is you really need to get buy-in from stakeholders on the limitations of this type of solution, because it's things that you can't fix afterwards. The solution can only be segment, not frame accurate. That is a big decision point. Because of this, break lengths have to be a multiple of segment duration. They can't be arbitrary lengths. That shouldn't be an issue, because your AdOps planners and your TX engineers, they should be able to build playlists that map to that. Assets then have to be a multiple of segment duration, and they have to be prepared in advance. The solution can only support integer frame rates, so 25, 50 frames a second, or 30 and 60. You've also got the limitation that the break structure has to be baked in on event startup. Due to all the optimizations that are run, we don't think it's possible to reorganize this on the fly and still maintain the live performance and not break the streams. We have implemented an emergency asset pool for compliance reasons, but all we do there is we say, okay, well, that asset still exists in the schedule, but we're going to say use this filler content instead of the real asset. We certainly don't allow the whole break structure to be reorganized. The other limitation that we adopted, and that was to keep the cost down and be able to get to market faster for our customer, was that the inserted assets only have a single language. So if you think about it, if you've got 6 regions that you're targeting, you can have 6 independent assets. Each of those assets can have a primary language that's different. That's not a problem. But if we had to support any particular combination and permutation of live stream multi-track audio configuration and insertable asset, checking that we always had a required and mappable language track was going to make things really complicated. And the last thing we wanted to be able to do was air a piece of content with no audio because we had no match. And so therefore we implemented this constraint. I'd also like to share some of the best practices we've learned. I recommend that you audit the Scuddy markers in the inbound transport stream. We grab ours with a TS listener and we insert them into a Splunk index. This allows us to very quickly, on a per event, per channel basis, look at what was sent. And it's invaluable because at times you will get ad breaks that don't fire, you'll get queries from the business, and you need to be able to triage quickly whether this was a transmission, TX system problem, or it was in the dynamic content insertion system. Even if it's not required for revenue management purposes, I would recommend providing an as-run report for each event. It will aid compliance reporting, and it will also serve as a first source of query handling, such as did asset X play out in region Y. I'd also recommend that you keep a copy of the manifest on event end. Certainly the HLS manifests were our go-to source of troubleshooting, and when we had things like the flash of live issue, it became very clear looking at the manifests what was going wrong. You've also got the issue with HLS and Dash, that you've got a temporal nature to the manifests. They're being refreshed all the time. So how do you diagnose a transient issue? So the issue we had with origins being out of date and content being in one request of the manifest but not in the second. What if your media sequence numbers are not rolling properly? How are you going to diagnose that? What if your live edge isn't moving properly? What if you've got flashing discontinuity tags appearing and then disappearing? All these things can be solved if you build a manifest grabber and then put some basic checks on them. And then finally, I can't stress this enough, but cache. All of this insertion processing is computationally expensive. You need to reduce the number of times you calculate the same thing. And you need to monitor the response times of your servers and the server load to make sure that you're staying within SLA. We do have some challenges remaining. It's difficult to experiment with different live settings now because we're very much tied to the VOD configuration. Our origins have become very large, some of them are bare metal. And if we want to go beyond sort of 8, 9, 10, 11 regional variations, I think we're going to have to shard the region groups across different clusters of origins. We'll have to then do some mapping on our caching layer to make sure the query parameter targets the right origin cluster. It's all doable, but these are things we may have to consider. And to support B2B syndication, we need to think about how we're going to reconstruct what might be needed as a transport stream. Reconstructing a transport stream for maybe our output with all of the metadata tracks, multi-track audio, caption tracks, that's not a trivial activity. We've also got changes in ABR protocols to deal with, such as low latency. They've changed the way the protocols work. We're going to need to build that in by doing some development work into the stack. But looking to the future, there are new capabilities in encoders that allow automatic or instantaneous switching between live and VOD inputs. So we're exploring moving the splicing from the packager domain to the encoder domain. This will benefit us by removing the segment constraint. Therefore, we can have frame accuracy. We can support fractional frame rates such as 2997. And it should make delivery of transport streams easier because we can just take a transport stream output from the encoder. In addition, the load becomes more predictable as it's not based on user demand and cache efficiency, but it's based solely on the number of regions that we're outputting. We do have some remaining challenges though. We haven't yet decided whether to use features of the encoder that will use in-band switching, so take the SCSI markers and switch automatically, or whether we need to build something that monitors the transport stream and then invokes the encoder API based on our own logic, so an out-of-band method. We need to apply the similar problem to suppressing and passing through markers, and we're working with Elemental to see whether we can build that into the encoder itself or whether that's something, again, we need to trigger via APIs. All of that is going to tell us whether or not we need to change the way the metadata is passed in. So either it's passed in the stream or it's passed in the playlist. You've also got to look at the fact that if you start basically switching before encode, then you're going to encode multiple times. You're going to encode for each region. And so that's going to have an impact on the encoder costs. But, that's probably trivial compared with all the benefits that you get. We're also closely following the SCSI standards work and the adoption of time signal as a replacement for splice insert. This allows the expression of different placement opportunity types, which different aspects of the workflow can then act upon, and it allows this to be specified within the SCSI markers. So, for example, it supports provider and distributor advertisement and placement opportunities. Using this approach may mean we can reduce the amount of out-of-band metadata that's required in the playlist and rely more on the markers that are inside the stream. So this wraps up my session. Thank you very much for watching. If you have further questions, please reach out via the email address that's on screen, and enjoy the rest of the conference.